Okay, these are some notes that we need to take from section 9.2, and this is exploration 1. So look in your book, if you're reading your book. On page 484, you need to go through this to make sure you understand what's going on with these special kind of series. And exploration 1 says construct a polynomial a sub 0, a sub 1x, a sub 2x squared, a sub 3x cubed, and a sub 4x to 4. So it's a fourth degree polynomial with the following behaviors. So I look on page 484 and you'll see p of 0 is 1, p prime of 0 is 2, p double prime of 0 is 3, p triple prime of 0 is 4, and p fourth derivative of 0 is 5. So we can take the derivatives. That's pretty easy. If we start with this polynomial, we take the first derivative. That's a constant, so that goes away, and it just becomes a sub 1, 2a sub 2, 3a sub 3x squared, 4a sub 4x to the third. And we take the derivative of that, then this is going to be 0, so we're going to have 2a2 plus 6a3x plus 12a to the fourth x squared. Take the derivative of this. This will be 0 because that's a constant. We have 6a to the third x plus 24a to the fourth, or 6a to the third, no x, right? And then the derivative of that's going to be 24a to the fourth x. And finally, the fourth derivative will just be the 24a sub 4. All right, a sub 4. I hope I didn't say a to the 4, I said a sub 4 to the x. All right, so you can see over here, those are the derivatives. Now, our stipulations was that the p of 0 is 1. Well, if 1 equals, if p of 0 is 1, that implies that if I put 0 in here, what do I get? All these terms fall out, so that means p of x is a sub 0, so p of 0 is a sub 0, so that implies that a sub 0 equals 1. Okay. If we put 0 in here for the prime, we're going to get a sub 1 is p sub 0, but if p prime of 0, so if we put 0 in here, we get a sub 1 is p prime of 0, but our stipulation is p prime of 0 equals 2, so that implies that a sub 1 will equal 2. And we take p double prime, that's going to be 2a sub 2, but our stipulation offer there is that p double prime of 0 is 3, so 3 equals 2a sub 2. And that would imply that a sub 2 is 3 halves. Should be double arrows for those implications, sorry about that. Okay, and p triple prime of 0, that's just going to be 6a sub 3. But we want that to be 4, so 4 equals 6a sub 3. Then that would imply that a sub 3 equals 4/6. And finally, if p double prime of 0 is going to be just 24a sub 4, that implies 5 equals 24a sub 4, which implies that a sub 4 equals 524. So we put this back in p of x. In other words, we know what a sub 0 is, a sub 1, a sub 2, a sub 3, a sub 4, by using the fact that when we take the derivative all these other at 0, all these other terms vanish. We just have these terms. And we want them to have these values, and we set them equal. We end up with these values for these coefficients, and we just put this back in the general form. So p of x would be a sub 0, which is 1. A sub 1x, a sub 1 is 2, so 2x. A sub 2 x squared, a sub 2 we found was 3 halves, so 3 halves x squared. A sub 3 we found out was 4/6, so it's going to be 4. A sub 3 is 4/6 x to the third. And then a sub 4, we found out that a sub 4 was going to be 5 over 24, so that's going to be 5 over 24x to the fourth. Now if you notice this is going to be 1, if we look at the denominators, I should say, we have a 2, a 6, and a 24, and those look like factorials. This looks like 4 factorial, 3 factorial, 2 factorial. If we think of this as being over 1, that'd be 1 factorial. If we think this is being over 0 factorial, we define 0 factorial as being 1. So we have factorial progression in the denominators. Now you could simplify this out, and this was a simplified form of this polynomial. But the idea is by taking these derivatives, and notice how we keep multiplying by, 2, then 3, then 4. When you're multiplying by 2 times 3 times 4 times 5, those are factorials. So we're getting factorials over here. And we do this equality situation. All right? Now there was another example now. Now we're just going to approximate this natural log of 1 plus x by a polynomial. Now, we're going to take repeated derivatives of this because that's what we do in this process. You can see we're taking repeated derivatives. All right, so I wanted to just let you take a look at something, a little idea about these qualities. I think you can see that over here. It's kind of faint because it's in pencil. But anyway, if you take a look at this, if you notice, we know that if y equals 1 over x, y prime is negative 1 over x squared. All right? If y prime is, that should be negative 1 over x squared. If y prime is equal to negative 1 over x squared, if I take the derivative of that, I'm going to get positive 2 over x cubed. And you can work that out, but that's what it does work out to be. Then if we take the derivative of positive 2x cubed, you're going to put that up in the top. It's going to be x to the minus 3. Then we're going to multiply minus 3 times 2 to get negative 6. Put it back on the bottom, and we're going to get negative 6 over x to the 4th. And if we take the derivative of that, we're going to get 24 over x to the 5th. And what happens is, and you can work these out, but you'll see that it ends up being of this form, negative 1 to the n over negative 1 to the n times n factorial over x to the n plus 1. So if we take these repeated derivatives of 1 over x, we get this progression, and you can see there again we have factorials in the top. And just progressive exponents in the bottom. 1, 2, 3, 4, 5. And this looks like 0 factorial, 1 factorial, 2 factorial, 6 factorial, and 24 factorial. Again, remember that 0 factorial is defined as being 1. Okay, so that's going to kind of help us as we do this second task, and this is example 1 on page 44, and it says, approximate the natural log of 1 plus x by a polynomial. So what we're going to do is we're going to try to come up with a polynomial. Now remember, I've talked about this before, okay, that the natural log of 1 plus x is a transcendental function. We cannot calculate that using pencil and paper. But polynomial functions like this we can calculate. If it was 0.6, we could just put 0.6 in here, 0.6 squared, 0.6 to the third, 0.6 to the fourth. It wouldn't be pleasant, but we need a pencil and a lot of paper. We could multiply it out. But if I asked you to find the natural log of 1.6, you couldn't do it without a calculator to punch out the number or a table of logarithms. So these polynomials are going to allow us to calculate natural logs, and that's actually how they calculated natural logs. That's where they came up with tables, and then that's how your calculator does it. So we want to construct a polynomial that matches the behavior of the natural log of 1 plus x at x equals 0 through its first 4 derivatives. That is, so my first derivative, second derivative, third, first derivative, second, third, and fourth derivatives at x equals 0. Now this is how we're going to find those derivatives. So let's take a look at what we're going to be doing here. To construct this polynomial that does match that behavior. So here's p sub 0, and that equals the natural log of x, and we want to find out its value at 0, which is going to be 0, and so a sub 0 will equal 1. Now remember what we did from our previous problem when we took the derivatives over here. We go back to exploration 1 because this is the general polynomial, so when we take these derivatives, this is what we get. A sub 0, a sub 1, 2a sub 2, 6a sub 3, 24a sub 4, and the 0 causes the other terms to go away. So these are still going to hold. for all situations. So if we take our derivative, in this case, before in our exploration when we were given the derivatives, now we're going to derive those, or take the derivatives and come up with those. So the first derivative of this will be 1 over 1 plus x, natural log, that's 1 over u du, and the du would be 1. So that's just going to be 1 over 1 plus x, at x equals 0, that's just going to be 1. And that equals a sub 1. We take the second derivative, that's going to be negative 1 over 1 plus x squared. At 0, that's just going to be negative 1, but that's going to equal 2a sub 2 when we took our derivative over here, if you can see that. So that's going to imply that a sub 2 equals negative 1/2. Our third derivative will be 2 over 1 plus x to the third positive. Remember, the signs alternate. Okay, at x equals 0, that's just going to be 2, but that's going to equal 6a sub 3. That's our third derivative. Result when at 0 is just 6a sub 3. So a sub 3 would equal 2 over 6. And at the fourth derivative, that's going to be, this is like 2 times, it's 3 times 2. You're just kind of multiplying that, because you're going to put it up on the top and make it negative and bring it back on the bottom. So it's going to give us our negative 6, 1 plus x to the fourth, and then at x equals 0, that's just going to be negative 6, which equals 24x to the fourth, or that implies 24x to the fourth. I'm sorry, 24a sub 4, excuse me, 24a sub 4. Oh, from over here, remember from over here from exploration 1, this is the same derivative, so that's not going to change. That's going to equal negative 6, so 24a sub 4 equals negative 6, which implies that a sub 4 would be negative 6 over 24, or negative 1/4. But leave it as 24 because we're going to be able to see the factorials. And those are implications, so they have double. It's a double arrow, not a single. Okay? So we can write p of x equals x. All right, 1, a sub 1 is, well, actually, a sub 0 is 0. So when we look at this, we've got a sub 0. This is our general form, a sub 0, a sub 1x, a sub 2x squared, a sub 3x to the third, a sub 4x to the fourth. And we figured our a sub 0, 1, 2, 3, and 4 by using our derivatives evaluated at 0. So we put these in, and a sub 0 is 0, a sub 1 is 1, a sub 2 is negative 1/2, x squared, 2, 6, x to the third, and minus 6 over 24x to the fourth. And if we could simplify this, and we get x minus x squared over 2, plus x to the third over 3, minus, and then 6 over 24 becomes 4. But if we look at these in factorial, this is like 0 over 0 factorial, x over 1 factorial, x squared over 2 factorial, 2x cubed over 3 factorial, 6x cubed over 4 factorial. So see the factorial progression in the denominator. That's going to be important. All right, so this is our polynomial approximation. Now let's graph these and see what happens. So we're going to graph the natural log of x plus 1, and then we're going to graph our polynomial approximation and see how close they are. I already did this. In y1 I put both these, and if you graph them, there's x plus 1, and there's our polynomial. And I can actually change this over here to a little darker line so you can see. So again, when we graph this, there's the natural log of 1 plus x, and then here's the x minus x squared plus x cubed over 3 minus x to the fourth over 4. And notice right around this range over here, they're very close. Now it changes over here, but right in this interval from negative 1 to 1, right around 0, which is the center, you can see how it's a good approximation. Almost the same. And that's what we're doing. We're trying to find ways of determining these transcendental functions by using polynomial functions which are algebraic and we can calculate.